I'm Sam Oler.
I'm Kellen Roddy.
I'm Josh Holtman.
And I'm Robert Frazee. And this is the first, and likely only, episode of QuikPhysik.
So let's cut right to the chase, since we only have the budget for 5 minutes of video.
Yeah, whose idea was that anyway?
Don't question the executives.
Anyway, so about gravity and energy. Energy makes things move, right?
Not exactly. Energy is the ability of something to do work, which is applying a force over a distance. Today we're going to be covering mechanical energy. An object has mechanical energy when it either has the potential to do work or is in motion.
Thus, there are two types of mechanical energy: kinetic energy and potential energy. Today we are going to focus mainly on two types of these specific categories: translational kinetic energy and gravitational potential energy.
Okay, I get kinetic energy, but what about potential energy? That seems kind of confusing.
Yeah, so it's best to show you an example. When it's rolling, it has translational kinetic energy.
Technically, it also has rotational kinetic energy too.
True, but that's a whole different ballgame. Anyway, if I hold it in the air like this, it has the potential or the possibility of moving if I drop it. See? It moved.
We all saw that. Kind of hard to miss.
Oh, be quiet, you.
Hey, we only got 5 minutes. Let's not waste any time arguing. Anyway, there's a mathematical relationship between the gravitational potential energy and the translational kinetic energy of an object.
The formula for finding an object's gravitational potential energy is pretty simple. It's just the object's weight times the height it is off the ground. Simple multiplication.
Whoa. 1 second. Always be careful where you choose the ground to be. In most cases, the ground will always be where the object stops moving, so the floor is almost always the ground.
Here's a quick clarification on gravity. Gravity does not always make things fall. It's an attractive force between any two objects. Gravity is technically pulling me and everyone else towards each other right now, but very slightly. In fact, the force due to gravity is so small, it's really only significant when one object has immense mass, like a planet.
But things get a little complicated. Well, more complicated than they already are. There's a difference between mass and weight. To find an object's mass, you divide its weight by the acceleration of the planet's gravity. Here on Earth, the acceleration due to gravity is approximately 9.8 meters per second. For every second something falls, it gets almost 10 meters per second faster.
Some of what he said might have gone over your head, and that's okay. For now, all you need to know is that if you're on Earth, an object's gravitational potential energy will equal its mass times its height off the ground times 9.8 meters per second squared.
And we're using SI units here, not pounds and feet. We're using kilograms and meters.
Okay, so this has a mass of 143 grams, or 0.143 kilograms. So we know that the object has a weight of 1.40 newtons.
The SI unit for weight is newtons.
I was about to say that. What are you doing? Anyway, we got that by multiplying the 143 grams times 9.8.
Now, if we were to hold this up, say, 2 meters, we'd have a complete formula. A mass of 0.144 kilograms, an acceleration of 9.8 meters per second, and a height of 2 meters. Thus, multiplying all this together, we get 2.80 joules of gravitational potential energy.
The formula for translational kinetic energy is a little bit more complicated, but not by much. It is 1/2 times the object's mass times its speed squared.
And a cool thing about the universe is the conservation of energy. Energy cannot be created nor destroyed, only converted from one form to another.
This means that the gravitational potential energy an object has before it falls is the same amount of translational kinetic energy the moment the object strikes the ground.
Doing all the math, we can figure out that the object is going 6.26 meters per second right when it hits the ground.
That's 14 miles per hour for you Americans.
So if you do not account for air resistance, the ball maintains the same amount of energy throughout the entire process.
This has been the first and most likely only episode of
QuikPhysik.